But today, I guess, I was just going to talk about some things that I find interesting. So I'm really fascinated by this idea that you can use the symmetries, right, associated with, use the topology of the symmetries that we use in physics, like rotation and Lorentz symmetry, in order to derive basically the physical content of our theories. So like, considering the topology of the rotation group led us to the conclusion that in 3 dimensions, there can only be 2 kinds of particles, the fermions and the bosons, that have integer and half integer spin. And those values of the spin sort of label the irreducible representations of the rotation group. And we saw that in 2 dimensions, the rotation group allows for representations that pick up an arbitrary phase. And that led us to the conclusion that in 2 dimensions, you can have, apart from fermions and bosons with integer and half integer spin, you can actually have particles with a arbitrary real number for the spin. And that leads to these exotic statistics that are popular in condensed matter now, like anyons. And these more exotic particles, again, just coming from topological properties of the symmetry group of rotations in 2 dimensions. And where I left, and I discussed a little bit more technically that what we did in class, we sort of took a group and argued, well, it must have some representation in terms of unitary operators on our Hilbert space. And that was a consequence of the Wigner's theorem. But where I sort of was talking about last time is that the more technical statement is if you have a group such as SO3, like the rotations, then what you do is you look at its universal cover, which is a group that's larger and that's simply connected, that doesn't have any of these funny topological properties where closed paths in the space are not contractible to a point. Where we saw in SO3 with the belt trick that there are certain kinds of paths that you can't contract to a point, even though they're closed paths, so they get you back to where you started in terms of the rotation group. So we had, closed loops in SO3 going from pole to pole in that sphere representation of the group elements that wasn't contractible to a point. So the universal cover is a bigger group that covers your original group, but it's simply connected. So it has a very simple topology associated with it. Namely, if you take any closed path in that space, all those paths are contractible to a point. So like a good example is the surface of a sphere, that you take any loop on the surface of a sphere, you can always contract that to a point. There are no holes in that space. There are no funny ways of making a loop that you can't contract. So that's what we did. Last time we showed that the covering group for SO3 is SU2, which is a complex unitary matrices with determinant 1. And we saw that the space of these guys can be represented as the surface of a sphere in 4 dimensions. So it's so SU2, all the elements in it, you can represent as points on a 3-dimensional, on a well, it's a surface, but it's a three-dimensional surface. It's S3. It's the surface of a sphere that lives in 4 dimensions. So lots of nice properties about it. You can Google S3. It's kind of an interesting space. It's got a lot of interesting connections to other topological concepts. So, but the way we showed it is pretty simple. We showed that any SU2 matrix, of course, has this form, alpha, beta, minus beta star, alpha star. And the condition that the determinant is 1 forced us to conclude that alpha squared plus beta squared is equal to 1. So the real and imaginary parts, they all add up to 1. So that's the equation for a surface of a sphere. You know, in 4 dimensions, because each one has a real and imaginary part. For a 3D surface of a unit sphere, this would be the equation, right? So that's just the analogy of that, but in 1 extra dimension. And then I talked about, of course, and so what's the point of the universal cover? This universal cover, again, this is the thing that has the faithful representations. So if you have a Hilbert space and you have those unitary operators, it's this group, the G bar, that for which there's just a 1-to-1 correspondence between the unitary operator and the group element. And usually the way the unitary is constructed for the universal cover is just that it's exponentiated generators like that. And so for SU2, it was these exponentiated Pauli matrices. You can write any element of SU2 as you know, an exponentiated a Pauli matrix plus the identity. That gives, so we saw that, you know, for these guys, you can also write the group element as I cosine theta over 2 plus I n hat sine theta over 2. So this you can just re-exponentiate using sort of the generalization of Euler's theorem. You just get exponentiated Pauli matrices. So yeah, and that's the idea, is that this guy is the one that has the nice representations, ones where, you know, the group elements correspond to what you would do with the unitaries. So there's no phase, no extra plus or minus sign or anything like that. And it's those representations, these faithful ones, then you can use the topology, essentially the relationship between the covering and the original group of interest to derive the projective representation. So for instance, we know that for SU2, this guy, this group covers this one twice. So there must be 2 different kinds of projective representations for SO3. One which, you know, picks up a minus sign under a rotation of 2 pi, and one which doesn't. And so that's the double cover property of this universal cover. Similarly, for rotations in 2D, you have the universal cover here is the real numbers. So so there you can cover this group, which is just labeled by an angle, you know, around, you spin around 2D, that's 2D rotations in 2D, and the covering group is the real numbers. So you cover the rotations an infinite number of times, because the covering keeps track of the number of times you wind around a point in 2D. And so there, that means you have like an infinite coverage of the group an infinite number of times. So you actually get an infinite set of projective representations, right, of SO2. And all of those different representations are all the different possible kinds of exotic particles, not just ones that pick up a minus sign after you rotate them by 2 pi, but also ones that pick up an arbitrary phase. And that's related in condensed matter to when you have two of these exotic particles and you exchange them, that would that's like a rotation. And in the Hilbert space, you not only can pick up a minus sign like you would for fermions when you exchange them, and we'll talk more about that next semester, but you can pick up an arbitrary phase, and that leads to all kinds of exotic statistics. Well, it's important for those of you who are interested in condensed matter. The other important group in physics is, of course, the group of Lorentz transformations, which this considers spatial rotations and boosts. And this is where we left off, I guess, the last time. And I just wanted to talk about this group sum, what it is. So it's, again, the rotations. So it has SO3 as a subgroup. And the generators for that are those T matrices that we had. But now, of course, they're 4 by 4 because this is, we're looking at a relativistic symmetry now, which, your time and space variables get mixed. So you have your time coordinate, which becomes sort of the 0th dimension of a 4 vector, right? Where the other 3 components of the 4 vector are the spatial components. So I mean, presumably you guys have seen special relativity at some point. Instead of position and time, you get a 4 vector where the time gets incorporated as part of a 4 vector, where this is now your coordinate, right? And that's what makes relativistic quantum mechanics hard, is because the time has a special privilege in sort of in the way we constructed quantum mechanics. We had unitary time evolution. We also had, very importantly, the continuity equation for the probability density. When we had the Schrodinger equation, we saw that it was consistent with a continuity equation for a probability density, which for us was the the wave function squared. It's this told us that the probability is a conserved quantity. This is much more difficult in relativistic quantum mechanics because the time and space parts get mixed, and it's not obvious you can define a probability density as just the psi squared that obeys this continuity equation. And we'll see that today a little bit. But any questions so far? This is sort of a recap of what we're doing. Okay. So you have the so the rotation. So this SO31 acts on like rotations that would act on the 3D vector. These guys, elements in SO31, they act on 4 vectors, and so they do things like apply boosts along various directions. So that's like adding, velocity along some spatial direction, or it also includes spatial rotations. And so the generators for the rotation part, of course, so if you can think about these as matrices acting on 4 vectors, the rotations don't do anything to the time component, but they rotate the spatial parts. And these guys are just the same T matrices we had before. You can go back to the notes and check them out. It's exactly the same, except there's this extra row and column corresponding to the time component of your 4 vector that gets transformed here. So again, this SO3 guy acts on 4 vectors, and hopefully you've seen that 4 vector at some point in your life. I don't know. Of course, it's not really the subject of this class, so I mean, this is just for fun. And you've got the TZ part. If you go back and look to how we looked at rotations, SO3, you'll see that these little mini guys, these are those T matrices that generated the rotations in 3D. That's all they are. And the thing about the SO3-1 is that the Lorentz group includes not only these rotations, but also boosts along the 3 directions. So it gives you a total of 6 generators. So it's a 6-dimensional group. I mean, you need 6 parameters to specify an element of that group. So remember, for rotations, when you do 3 angles, or if you want a single unit vector and an angle, that's also 3 parameters. Here we need the 3 angles for a spatial rotation, and then a vector, arbitrary magnitude, corresponding to a boost along some direction. And the boost generators are as follows. They're kind of like the spatial version of, or sorry, the time component version of the rotation generators. So they look kind of similar, except the eyes have the same sign. This also makes the group kind of funny because you see they're not Hermitian, these generators. So that's a kind of annoying, but fundamental property of the Lorentz group. And so these are these 4x4 matrices, and of course you can work out the commutation relations. And again, it's something I didn't really emphasize very much. So the commutation relations that you get, they're going to be, so they are local properties of this group. They have to do with how small transformations behave, right? Remember, we derived commutation relations by looking at the exponentiated generators and then looking at small angles for the rotations, and we derived, actually that's how we derived the generators to begin with. Well, now I just gave you the generators. So the point is, those commutation relations, those are, that's the so-called Lie algebra associated with the symmetry group. And the Lie algebra is a local property. So it's actually going to be the same for the group and its cover. So like the commutation relations of the T matrices are the same as the commutation relations of the Pauli matrices of the covering group generators. So once you have the commutation relations, you can use those actually to figure out what the universal cover group is, because you can just take those, because those commutation relations will hold for the covering group as well. So here, the commutation relations are a little bit awkward because 2 boosts, I don't know if you've seen this at some point, but if you boost in one direction then another direction, that actually generates a component of rotation, right? It sort of makes sense. You boost in 2 directions, that kind of sort of imagine in your head. It's hard to see, but I mean, I don't know how your intuition is with special relativity, but 2 boosts will generate a rotation. So apart from these guys, these commutation relations, and between the B's, there's also a commutation relation that's sort of similar. So again, two boosts will generate a rotation. So actually these commutation relations look like this. Oops. You see it's a product of two boosts will give you, this commutator will give you a rotation generator. And then there's also, if you have a rotation and a boost, then that gives you another kind of boost. Also should make sense, right? You rotate and boost, then that's another, it's another boost. So, but you can just work these out, by just working out the matrix multiplication. But here you go. This is the Lie algebra associated with SO31, the Lorentz group. It tells you, the commutation relations between generators of rotations and boosts. But this is a bad set of generators because they don't commute with each other, right? You get two T's, you make a T, that's fine, but then T's and B's, the boosts and the rotations don't work well together. They don't commute, so that's bad. But you can actually do a transformation that gives you a nicer set of generators, and it's the usual thing. It's a transformation we've seen sort of over and over again. It's very similar to the transformation between sort of Cartesian components and then the spherical components of a vector. What you do is you define new generators xi plus or minus, and these are kind of like the left-handed and right-handed m plus or minus 1. That's the analogy, sort of, but of course it's different. It's a different group, but it's sort of similar, same flavor, I guess. But basically what you do is you just take linear combinations of the rotation generators and the boosts with a complex I here. You take these guys, and then the commutation relations for these guys are much cleaner. They're as follows. So plus or minus has to do with which combination you take plus or minus. And the plus or minus guys don't commute, or they do commute, sorry, with the opposite type. So a plus and a plus will give you another plus, a minus and a minus will give you another minus in this commutation relation. If you take a plus and a minus, or a minus and a plus, you always get 0. So that's good. You have two sets of operators, right? The x plus and the x minus, which amongst themselves, they satisfy these commutation relations, and then between themselves, they don't interact. They commute with each other. So what does it mean? And look at this. It's two copies of these angular momentum commutation relations. It's like it's two copies of generators that behave just like SU2. So this tells you have two independent copies of SU2, because we know this is the Lie algebra for SU2 or SO3. So you can see now that this group, SO31, by looking at the commutation relations, we see that the covering group should be at least isomorphic, should be a 1-to-1 correspondence with SU2 cross SU2, two copies of SU2. More technically, the actual universal cover is actually SL2C, and there's a particular mapping between SO31 elements and then SL2C, which this is all invertible matrices, 2x2 matrices, complex entries with determinant 1. But that will get us into the weeds with space-time transformations, which since this isn't really a class on special relativity, I won't get into. But I've now shown you with some considerations of just commutation relations, which is part of our class, that you can actually conclude what the representations of SO31 should be, right? We were able to derive that the commutation relations associated with SO31 generate two sets of these operators that behave just like angular momentum. So representations of that group should be labeled by, right, two copies of angular momentum. They fall into just two copies of SU2, or if you want, they're labeled by 2J numbers. So that's great. That labels all of the representations of the Lorentz group. So in particular, you have, you have things like the 0,0 representation. That's just like a scalar that doesn't transform at all. You then have things like 1/2 0 and 0 1/2 representations, right? And those correspond to two different kinds of spin 1/2 particles, which are related to the right and left-handed fermions. So the structure of the topological structure, or I should say, the representation theory associated with SO31 will tell you about the kinds of particles you get in relativistic theory. So this is sort of closely related to how Dirac proved the existence of antiparticles by considering relativistic quantum mechanics. It just comes from, fundamentally it comes from the sort of, I'd say the topological properties of the associated symmetry of the Lorentz transformations. Well, I mean, it's not topological in the sense that, it relates to the universal cover of the group. But really, again, these commutation relations are local properties. The commutation relations connect the group to its universal cover because locally they look the same, the group and its universal cover. So yeah. So what about the, any questions though about that? Okay. I'm going to clear this then. So, so what about the Schrodinger equation? The issue is that the Schrodinger equation is not a Lorentz invariant equation. So it's not invariant under that group. It's a problem, right? Because the SO31 it mixes the spatial and the time components. So, you know, the Schrodinger equation we had is not compatible with that. So we have to think of some other equation that is Lorentz invariant, and that's sort of historically how, you know, relativistic quantum mechanics developed, is that, well, we at least have the correspondence principle, which kind of tells us that if we were to have a sensible equation describing relativistic quantum mechanics, it should at least obey the special relativistic momentum energy relationship, which is that E squared is equal to, you know, P squared C squared plus M C squared squared. Should at least satisfy that. And then we know that the energy is related to generators of time evolution. So we should still have that the energy corresponds to I h bar d dt. We still have that because that's what energy is, right? It's the operator associated with time evolution. So we should still have this correspondence. And we should still have that the momentum operator is related to spatial translations. So it should still correspond to, in terms of the position space representation, right? It should still correspond to minus I h bar times the gradient operator acting on, you know, the wave function, which is the spatial representation of the state. So we still have that. And so the idea is that now, unfortunately, these two things are going to have to be combined in special relativity, right, into a 4-vector. So we can define the momentum 4-vector. That should correspond to I h bar. And then in one component, there will be just a time derivative. And then this minus sign goes away because of the sort of Lorentzian signature. You know, the 4-vector, the spatial and time components come in with opposite signs. So the associated operator associated with the momentum 4-vector would look like this. So again, this is the kind of quantum mechanical operator corresponding to the momentum 4-vector. And so then what would this relationship tell us? Again, we can rewrite this as in terms of the 4-vector as the momentum 4-vector as p mu. Again, this is Einstein summation convention. I don't know if you've seen this. You get to sum. These are 4 vectors, so you sum the components, multiply the components, and sum them, and then you stick in a metric, which gives you the opposite sign between the time and position pieces. I don't know how many of you have seen that, but doesn't matter too much. It's just this equation is equivalent to the following. And so what it means is that if that's the sort of classical equation, then whenever we do the quantum mechanics, the correspondence principle will tell us we'd expect, you know, the quantum mechanical version of that equation to also hold. So that leads us to the following, that if you combine these two ideas, that there's the classical version, which is that equation there, which is just this E squared is equal to, so this energy momentum relationship. If you combine it with this idea that the operators, the associated operators with those quantities are still, you know, come from time and position translations, then the only natural equation that's going to be Lorentz invariant, that's sort of consistent with both this quantum mechanics and this classical relationship, is that minus h bar squared d mu. And now these guys are the gradients in 4 dimensions. So there's a time derivative in here too, acting on the wave function now as a function of a position 4-vector. the 4 vector has a time component too. That's equal to m squared psi x nu. So, and if we use natural units, C is equal to h bar is equal to 1. Another way to write this would be 2 derivatives of time minus 2 derivatives of space. This is a function plus m squared acting on psi is equal to 0. And this is the Klein-Gordon equation. And I believe historically it's actually the equation that Schrodinger wrote down first before moving on to, his equation. I believe that's the history of it. Because see, it's kind of easy to derive from special relativity. All you need is just this correspondence between energy and momentum and the associated operators in position space. And then from there, you can sort of conclude that this is the only kind of equation that is consistent with the Lorentz invariance. Now, if you apply boosts to this and rotations, it works nicely. It remains invariant. Rotations, of course, are easy because this is rotationally symmetric, the Laplacian part. So that's the Klein-Gordon equation. That's kind of like a relativistic Schrodinger equation, but it's bad. It's bad because it has 2 time derivatives, and there's no natural way of interpreting it, of interpreting a probability density. You sort of lose the probabilistic interpretation of the wave function. It's no longer the case that you can consider, this object as a probability density. I'll say more about that in a moment, but any questions on this? This is sort of the historical way in which the Klein-Gordon was derived, in my understanding. No? Okay. So it's a bad equation. Well, it's fine. It actually does actually describe certain kinds of physics. Describes the pions, I believe. But in any case, it's not a nice equation from the point of view of interpreting it like we interpret the Schrodinger equation for 2 reasons. First of all, well, you can see immediately why 2 derivatives are bad. So what's nice about a first order equation in time, right? It's sort of fundamental thing. A first order equation means you can specify the initial condition that you want for your wave function. You specify some preparation of the system, right? Some initial preparation, and then you can integrate that time derivative, just one of them, to evolve the wave function in time, right? And that's how we interpret it, right? When we did wave packets and things like that, we had an initial wave packet. We had a first order equation, the Schrodinger equation that describes how it evolves. You can stick it into Mathematica. I showed you that in class. And you just evolve the wave function in time. But a second order equation is not like that because you have 2 time derivatives. So now you need 2 different boundary conditions in time. So that's a big problem. So it's no longer, you can no longer even interpret it as, in terms of like a wave packet that you prepare and then evolve in time. There's no way to do that. And if you look for plane wave solutions to this, which, this should describe some free particle with some kinetic energy, that leads to even more problems. There are plane wave solutions you can find, but they look like this. They look like minus E, and then there's a time component, and then there's the minus px that we're familiar with. But the issue is that there are 2 values for the energy of this thing. You can get plus or minus square root of p squared plus m squared. two different solutions. On top of, so remember, before we had plane waves that go left and right. Those are two different signs of the momentum, but now we have states with negative energies. And that's a big problem too, because you can sort of generate energy spontaneously in a sense, because you can, well, it becomes very difficult to interpret, right? What does a negative energy mean for a free particle? So it leads into all sorts of interpretational issues. So that's a problem too, is the fact that you have two different kinds of plane wave solutions, one with positive energy, which is sort of more reasonable and might correspond to the kinds of scattering states that we saw for our relativistic, non-relativistic Schrodinger equation, but now you get negative energy states, which you have to deal with somehow. And I think more importantly, at least in my mind, is the fact that remember in the OG original Schrodinger equation, which was, I'm writing it in these natural units, or h bar and set to 1, that looks like this. This guy, we can interpret it as a continuity equation for the probability density, because the way you do that is, I didn't show you this, but this is a nice kind of quick way to derive the continuity equation. You take this equation, and if this is equal to 0, then certainly psi star multiplied by the same equation that should be equal to 0, because this is equal to 0, but this actually gives you the continuity equation. This tells you this is, if you expand this out and start taking the imaginary part, you can show that this is just equivalent to the time derivative acting on psi squared plus the divergence of this seemingly complicated expression, but it's not, because it's just a probability current. So the original Schrodinger equation, so I wrote it in blue, the non-relativistic one, we can interpret it as a continuity equation. If we take the imaginary part of the equation multiplied by the complex conjugate of the wave function, then this equation is the same as this. It reduces to dt of rho, which is equal to psi squared. So it's positive, right? Plus the divergence of some vector, which is given by this combination, which is just the probability current. So the Schrodinger equation is equivalent to a continuity equation for the probability density. And that's great, because that means we can interpret the square of the wave function, right, as a probability density. It's the probability density associated with measuring the particle at a particular location. Klein-Gordon equation, it's not like that at all. Yeah, you if you try to do that, let's try to do it, you would take the imaginary part, right? Let me put it back to red. You take the imaginary part of psi star, and then you would, well, sorry, this is, you would try to psi star times the Klein-Gordon equation, which is this thing up here, to get dt squared minus Nabla squared plus m squared psi. That should be equal to 0, right? And now if you expand stuff out, you do get something that looks like a continuity equation. So you do get something that's, some real number plus the divergence of some current-like thing, but they have different expressions. This is just expanding this out, taking the imaginary part. What you'll find is the current looks the same, so that's good. It's still 1 over 2 mi psi star psi minus psi, like that. It's the same as for our original Schrodinger equation, but the rho now is gross. It's, I think, I over 2m. And this is a real number because if we take the complex conjugate, these two terms exchange, but we pick up a minus sign from the I. So it is real, but the problem is this thing is not always positive. So you can get negative probability density. It's not good. So we can't even interpret it as a probability density. It's a big problem. So the Klein-Gordon equation is not a very good Schrodinger equation for that reason. It turns out that you can actually interpret rho as a charge, and then you can have positive and negative charge, and it's okay because then rho doesn't have to be positive anymore. You don't have to interpret it as a probability density, but it's sort of unsatisfying. So what happened then is that people spent a very long time trying to figure out if you can solve these issues with the Schrodinger equation, with this Klein-Gordon equation, by trying to take its square root, because then you might be able to pick out one of these branches individually for the energy and just look at just a positive energy solution. And that would be very convenient because if you somehow do manage to take the square root of this equation, you might be able to get a first order equation in the time variable. So the idea was you rewrite the Klein-Gordon equation like this. And then you try to take the square root. Well, it's very, it's not a very well-defined procedure. It's not very good. But if you were to do such a thing, well, you got square root of -1, that should give you an I, and then somehow you get one derivative now with respect to time, and this should be plus or minus square root of m squared minus both squared psi. And then so you could try to do that, but the problem is that this is a very bad operator right here. Remember, any function of an operator, you have to do a Taylor series. So this would include arbitrarily high powers of these derivative operators when you Taylor expand the square root. But people spent a lot of time messing with this. And what Dirac managed to show is that you can actually factorize the Klein-Gordon in a nicer way. You can kind of complete the square, much like we remember looked at the harmonic oscillator and broke up p squared plus q squared into a dagger. Something quite similar happens. See, the same in theory, in theoretical physics, same sorts of tricks appear over and over again in different disguises. So this equation, what Dirac was able to do is show that you can actually factorize it into two linear pieces, where this is some operator to be determined, presumably having something to do with a single derivative. I was able to show that you can factorize the Klein-Gordon equation like that. And then if this is true, if you can really break it out into a product of factors, then what you can do is reduce this to a single equation where it's just p minus m acting on psi is equal to 0. That's what he was able to do, essentially, is factorize the Klein-Gordon equation that way. And he did it, and he recognized that the only way to do it is by allowing these p's, these operators, to live in a four-dimensional space, to be four-dimensional matrices, essentially. And you can probably you can derive something like that. It has to be the case from representations of SO31, but I've yet to see a good resource that does things in a different way from this. I'll try to think about it maybe for next semester. But anyway, what he showed is that the p operator that factorizes the Klein-Gordon equation like that is actually I gamma mu, where these are 4x4 matrices, partial mu, where these guys are, the 4-vector the 4-vector gradient, the spatial derivatives and the time derivatives. And what are the gamma matrices? There's lots of ways to write them, but one way is the following. They're actually just related to the Pauli matrices again. So this is a 2x2 identity here, and the time component is just the identity, and the XYZ components, they're the Pauli matrices again. And this is why I know, you can derive this kind of thing from representations of SO31, because we know that we saw that SO31, the representations are broken down in just 2 copies of SU2. And that's what these guys are. These are the generators for SU2, right? So this is, unsurprisingly, these gamma matrices are related to having 2 copies of the Pauli matrices. But I think the way that Dirac did it originally is just showed that the only way you can factorize the Klein-Gordon equation like that is if you make P a 4x4 matrix. There's no other way to get things to multiply out correctly so that this multiplies out to this nice Klein-Gordon equation. So indeed, he's able to show that if you introduce these 4x4 matrices, that then the Klein-Gordon equation, I'm going to combine the spatial and time derivatives into this box. It's called the D'Alembert. You've seen it. That thing is equal to I gamma mu partial mu plus m I gamma mu partial mu minus m times psi is equal to 0. So he's able to factorize, kind of, do the harmonic oscillator thing, break up p squared plus m squared, p squared plus q squared into like 2 linear factors, like this A and A dagger in a sense. It's different, of course, very different, but morally similar, I would say. And so now, now you can write down an equation, right, that's linear in time, because you only have to look at one of these pieces, like this one. And this is the Dirac equation. But you see, now the psi has to be promoted, right, from just a single function. Now it has to, it's operated on by a 4x4 matrix. So this has to be four-dimensional vector. And that's called a Dirac spinor. It's 4-component vector. So there's a wave function each component. And we sort of know that that has to be the case, right? Because again, we know that the representations, I erased all that, but the irreducible representations of SO31, right, are labeled by 2 angular momenta. And so, unsurprisingly, this 4-dimensional Dirac spinor guy, it transforms like, well, it's a little bit more technical. Basically, it's the 1/2 representation. It's two spin 1/2 particles that are incorporated in this 4-dimensional Dirac spinor, and that's the you can think about it as the spin 1/2 particle and its antiparticle, essentially. But that's more details than I'm willing to go into, and I did want to spend just a teensy bit of time on review. But if there's any other questions you have about this, I'd be happy to try to answer. Of course, I'm not an expert. Again, I do biophysics. Quantum mechanics is pretty far from what I do, but relativistic quantum mechanics maybe is even further in a sense. But we'll see once we get to field theory that it's actually connected back to statistical mechanics. Maybe we'll see that next semester. Incidentally, the reason we don't do this kind of stuff very much in this class is because true relativistic quantum mechanics will very rapidly lead you to the conclusion that having a fixed number of particles is just not a good idea, right? Because if you are at high enough energies, where relativistic effects are important, then very hand wavy, but the energy momentum relationship, right, tells you that mass is related to energy. And so it's, what actually happens if you're sufficiently high energy, you can create mass. So that creates, that there's pair production that occurs at sufficiently high energies. And the kind of quantum mechanics we do in this class assumes a fixed number of particles. There's no nice way of having particles pop out of nowhere. Even when we do many particles, right, we'll always assume sort of a fixed number, but at high enough energies, you get spontaneous production of particles. And so, the only consistent way of dealing with that is by introducing fields. And so relativistic quantum mechanics rapidly transitions to a quantum field theory, which is why this kind of stuff, the Klein-Gordon-Dirac equation, it's sort of a little bit out of style. You don't see it very much in classes anymore. It's because it doesn't really naturally fit in anywhere. It can either fit in at the end of a quantum class, or it might fit in at the beginning of a quantum field theory class. But sort of a little bit of a weird topic, I guess. Any questions?